Today we're going to talk all about the metric system. So what things does it contain? How do we abbreviate units? How do we measure things within the metric system? Now in science we use the metric system because quite frankly it's just easier to use and the rest of the world uses it. But before we can use it ourselves, we have to learn a few details about it. Again, how do we measure things? How do we measure volume? And all those different things. So what is the metric system? The metric system is a system of measurement that is based on the number 10. Now this number 10 is really important. These units of 10 are given with prefixes such as kilo, hecto, deca, and I'll tell you what this base unit is in just a moment here. Deci, centi, and milli. Now, the number 10, as I said, was really important and is abbreviated by these prefixes. So with the number 10, for the system is built on number 10, basically what that means is we'll start with 10, and then if we go up another unit, it's 100, and then 1,000. It's basically just multiples of 10. You can multiply each thing by 10. So, for example, we have kilo here, which is really going to be 1,000 times bigger than this base unit. Deca is going to be 10, hecto is going to be 100, and then 1,000. We're just adding that 0, or a multiple of 10. It goes in the opposite direction with these ones to the right of the base unit, and we'll get a lot more of these details in a little bit later on in our metric system unit when you talk about converting between these units. Now I mentioned I talk about this thing called a basic unit. And so the basic unit is the standard unit used for the given measurement. So for measuring length, we'll have the standard unit. So for example, the meter, or abbreviated the lowercase m, is the standard unit used to measure length. Now you're sort of probably familiar with the meter. You've probably seen them around my classroom or just in general. They look a lot like a yardstick, but they're different in a very specific way. And again, we'll talk about that when you practice measuring things. So that basic units, they don't have, or they won't have the prefix attached to them. So a prefix is going to be that piece that comes right before. So we already mentioned them. There's this kilo, centi, deci, etc. Right? There's a bunch of them. So a basic unit example would be the meter. Right? So that's our blue word there. And then our unit with the prefix is going to be kilo, and then we have meters. So we basically just put that prefix, that red part, and just attach it right into the front. Same with any of them. So if you have decimeter, centimeter, and that tells us basically the magnitude or how much of that item we have. 1 kilometer is greater than 100 meters, simply because that word kilo is basically a shorthand way of writing 1,000. And the nice thing about that is it helps keep our numbers smaller, so we don't have potential errors of, oh, I forgot to write a 0 or I forgot to do this. It helps prevent a lot of those typos, and it can save you just a little bit of time. So it's kind of nice to have that. And as we get to later, it also will make converting between all these different units pretty easy as well. So if you haven't done so already, please make sure you have your vocabulary books out and open to our first lesson, which is that 3.1, that first section we're going to talk about with the metric system. And you notice the first word that we're going to have for that is the one I have right here on screen, the International System of Units. We oftentimes abbreviate it SI, which you're probably wondering, well, what the heck, why is it SI and not IS? And that's because it comes from actually the French, who were the ones who originally came up with this idea of the metric system. And that's what they have going on right here. And that's why in French, right, it's the Système International right here, which is SI. Now, when you translate that, that turns into international system, and in this case of units. So that's kind of why that's the case. So what is it? It's, well, a system of units used by scientists to measure the properties of matter. It's a very specific branch, so to speak, of the metric system. It uses the metric system. It's basically, scientists have said, okay, we need to have this universal system of measurement. We need to have a way that when we all communicate, we all understand the units. Otherwise, it's really hard to understand what you're trying to say. So we took things from the metric system and said, okay, we'll use these. Now, when we report our facts, our figures, and all these things, we all understand what we're saying. We know when we say something is 20 meters long, about how big that is. And that really, really helps. So that example being a system of measurement that allows scientists to compare data and communicate their results. Again, so it allows us to compare data as well a little bit easier. So now if I say, oh, I got 20 meters for whatever thing we were doing, I said, oh, cool, I got 18 meters, we're pretty close. You can imagine if we had a bunch of different measurements, like say we still measured with lengths of a hand, which was a thing, then I could say, oh, well, I got 12 hand lengths. And they're like, okay, well, I got 35. And for all we know, they could either have larger hands or smaller hands, and that distance could be much different than what I found, or maybe I have bigger hands. It's not a set standard, and that's what's really important. That set standard allows us to actually have these equal units and really give meaning to our answers and easily communicate them without much chance of error, which is really, really important. So if you hadn't figured it out, right, we got my definition right here for that SI system. We got the example for you right here. Now here's kind of the picture that I got going on. Really, this is just a table of those different SI, well in this case prefixes, that will attach to those base units I just talked about prior. And we talked about those prefixes as well just a while back. I just added a couple more, and you're right, so now you got mega, and we got micro, and we got nano, and then they add those factors on here too. So these are probably the ones that are most commonly used. You don't tend to go too much far past here. You get something called pico at the very, very, very bottom, and that's really, really tiny. But those we generally we won't get into, and they're not used very commonly, except for looking like at subatomic particles. Now you'll recognize all of these symbols in the sense of you'll know that they're letters, right, from our alphabet. The only one you won't recognize is the micro, and that's actually the Greek letter mu. The reason we use it is because that's the Greek letter M, basically, right? So we have mega, we already used our capital M, and we have our lowercase m for milli. Well, we have micro, like, well, that's an M, we need something else to put there, so let's take it from the Greek alphabet. So it doesn't really look much like an M. I mean, maybe kind of if you squint a little bit, but really to me it looks more like a U with a little tail in the front. And that basically just is the abbreviation for micro, which is going to be a really small unit. And you can see these factors on the side to give you an idea, those factorials. So if we have something that's like kilo, so kilo is 1,000, that means we're really going to have those 3 zeros. Basically, it's 10 multiplied by itself 3 times, which will give us 1,000. Now, the next word that we're talking about, length, well, you know this, right? It's the distance from one point to another. Right? Oh, how far is that? Oh, probably 3 meters. Of course, you probably don't say meters, you probably say feet or something like that. We want to try to make sure we're getting into the habit of saying a meter or something of this base unit. So in the SI, that basic unit of measurement is the meter, right? So when I say basic unit, I'm just meaning in general we'll measure things in meter, and it actually happens to be also that base unit. There's really only one example where the base unit is actually not the SI for our purposes, and I'll make sure to highlight that when we get there, but otherwise they're the same, which is pretty helpful and makes sense. It's that middle unit, so makes sense to kind of have that as the standard unit that we'll report it as. So, right, so we have that distance. Now that's just really going to be our point A, right? So if we have like a point right here and say we go on a little walk, and so let's move that distance to point B, right? So now we could measure this length. I could, grab onto this meter stick that I have here on screen if I actually could, and then measure what that actual length was and give you an answer. And, say, oh, maybe it's 3 meters or 2 meters or 70 centimeters or something of that nature. So it's just a distance between 2 points. All right, so moving right along, we're going to have our mass. Now, mass is a measure of the amount of matter in an object. So everything that exists has matter, and so that's why I have my fun little science cat over here, right? You have mass, you take up space, you matter. Anything that takes up space is going to matter, in the sense of it has mass. In the SI, the unit of measurement is kilograms, abbreviated kg. And so now this is the one that's different, right? So note, base unit is grams. So this is really important later when we start talking about converting, why that base unit is so important. The SI unit is kilograms, and that's just because a lot of things will measure way a lot more than a gram, because a gram isn't, it doesn't have that much mass. Another thing I want to make sure I want to highlight the fact is mass is not the same thing as weight, okay? They're not the same thing, and that's a really important thing to make the distinction of. We'll talk about what the SI for weight is in just a moment here. Mass is just simply about the amount of matter. That stays the same no matter where you go. Your weight can change based on your location, especially when we're talking about different planets and things like that. And so we'll get into all that in just a moment here, but I just want to make sure I really highlight the fact that mass is not weight, and kilograms is going to be that SI unit, where grams is the base unit. That's the only one that they're actually different. Alright, so next we're going to talk about weight. Now, remember, I just said weight is not the same thing as mass, and that's absolutely true. Generally speaking, something that has a large mass will in fact have a greater weight. And we're talking about just staying on Earth, that can be generally true. If something's more massive, it'll have a greater weight, because gravity is more or less constant on Earth. So we just associate with, okay, this is very massive, that's going to have a huge weight. But that's not always true, right? So the definition of it, of weight, is the measure of the force of gravity acting on an object. So the example of this being, in the SI, the basic unit of measurement is newtons. Now you've probably heard of him, and a lot of you have seen my Newton's Cradle and have played with it. That also bears his namesake. Newton was a wonderful physicist for us who gave us a lot of different things, including his 3 laws, and we'll spend time talking about those later in the year as well. Really, the idea is every particle, every piece of mass that an object has, gravity will have an effect on it. In our case, our planet has a certain attraction, has that gravity. Now it pulls on those objects. The more mass, the more pull that it can have. So, just a random example, my weight on Earth is around 560 newtons. This isn't like my actual weight. This is just, general example. Whereas on the moon, my weight is actually 90 newtons. So weight can change. Mass cannot. Right, so my weight in outer space is 0 because I really don't have any gravity, nothing that's really measurable. That's why you just kind of float and hang out. Whereas my mass, in this case, is always that 60 kilograms. Right here, or 56 kilograms. My goodness, where did I get 60? My weight can change based on location. My mass will not change based on location. Mass does not change, it stays the same. The only way it'll change is if, like, I lost an arm in a tragic space accident or something. Then my mass could change. But my mass, will always stay the same as long as I'm still me as a whole object. Now, the next one to talk about is volume. Now, you know what volume is in the sense that you can figure it out. You can say a box and look at it and do length times width times height, right? That's going to be an equation that we can use. So now the example, or the definition of volume, is the amount of space an object or substance takes up. So this is the amount of space it takes up. So the example is in the SI, the basic unit of measurement is the liter. It won't always be in liters. Sometimes we'll have more physical, so we could have like meters cubed. And so when I say meters cubed, what that means is I have, say, meters, but then I have the little 3 on top. And basically that means is I have like that length, that width, and that height. Those 3 different measurements I multiplied, that creates that meters cubed. That's where that comes from. And that's going to, so this type of, where we have that cube, that's going to be more for physical things. So in this case, a lot of times we're talking about liquids, but if we're reporting something as a physical amount, then generally we want it in a more physical measurement in meters or centimeters or things like that. And sometimes you'll hear, a lot of times on shows, a lot of those medical shows, you'll hear, sorry, here's kind of our fun fact, I need 100 cc's stat. You may hear that and you're like, well, what the heck is a cc? Well, cc is 1 centimeter cubed, or how you'd read that, a cubic centimeter. So we have those two c's right here, and then so they just say cc, right? You can imagine you can run around all day saying I need 100 cubic centimeters. That'd be kind of annoying, so it's abbreviated to cc's. So it's kind of just an interesting little fact. But the SI unit in general is going to be liter. And over here on the side, we got that image, right, of our measuring cup, and a lot of times we'll use a graduated cylinder. This has graduates on it. Graduates are these little markings here, okay? And that just tells us how much, and in this case you can kind of see it real tiny, it says milliliters, so that means we have this going up. So this would be like 500 milliliters right here. Now, the very last one we have to talk about is density. So density is the measure of how much mass is contained in a given volume. This one incorporates two of the passwords we've just talked about. It is going to incorporate our mass, and it is going to incorporate our volume. So it takes both of those ideas and kind of puts them together into one concept. So the example, in the SI, the basic unit of measurement is kilograms per cubic meters, or this unit right here, kg/meters cubed. So really what this is saying is there's a certain amount of mass, remember kg is our mass, a certain amount of mass per unit of volume, meaning for each meter cubed, there's so much amount of mass, amount of matter taking up space. So this picture that I got going on down here for density is going to have these two different blocks, each one filled with a certain number of these green spheres, these green balls. Now, one is pretty tightly packed, this one on the right, and one on the left is less tightly packed. You see, because there's a lot of space kind of in between here, that there's not a whole lot of space, it's full. So if I were to ask you, well, which one's more dense? Well, you hopefully are thinking the one on the right. There's more things, so if each one of these green spheres I got over here have a mass, well then there's going to be more of them having a more, so they'll have more mass in this box. And now you could agree that these boxes are, or cubes rather, are they're both the same size. So that means we have the same amount of volume, but this one has more in it. I mean, it's going to be denser. And this is what explains, and I'll show you guys some density cubes later, why some objects are small but seem to be extremely heavy. Right? That's because they have a lot more mass, and since gravity is constant on Earth, then they're going to have a greater weight, right? Remember again, mass and weight, two different things. And so we'll look at that. So there's substances like brass and copper that are pretty dense. They're pretty heavy for the size that they may be. Whereas there'll be other, not that they always have to be metals, but others would be aluminum is pretty light. And that's why they like to use aluminum in a lot of structures, that because it's fairly strong still, and it doesn't rust, so it has a lot of those benefits, but also just because it's fairly light. A lot of boat lifts, if you go to a cabin, are going to be made of aluminum because now they're a lot easier to move in and out of the water. A lot of those types of things they like to have made out of aluminum because it's considerably less dense than, say, steel, which then having that same amount would have a huge mass, and in this case, then also have a greater weight.